Just like we saw some basic properties of finite series, there are corresponding properties for summations over finite sets. So this proposition is about such properties, and just like that other result where we had properties of finite series, this one also has parts. So the first part is this: if X is the empty set and f from X into the set of real numbers is a function, that is, f is the empty function, because if X is the empty set, then there can be only one function from X into R, that is the empty function. Then we have this summation of f of x as x varies over x is 0. Okay, so that is the first part. It corresponds to part A in that other result where we had basic properties of finite series. Then part B, if X is a singleton set, that is, if X consists of a single element, if X consists of a single element, say X consists of the element X naught, and f from X into the set of real numbers is a function then we have summation of f of x as x varies over our set equal to f of x naught. So that is part B. Then part C, I think, is, yeah, it's substitution. This is substitution part 1. There are two substitution laws. If X is a finite set, now X is any finite set, not necessarily empty set or a singleton set. X is any finite set. F from X into R is a function, and G from Y into X is a bijection. That means the hypothesis starts off just like how we would start when talking about a summation over a finite set. We have a finite set and we have a function from that set into the set of real numbers, and then we talk about a sum like this. But now additionally there is another function g, which is a bijection from y into x. That means y is another set which has the same cardinality as x. Then we can write something. Let me just clean this part first. In place of that original sum, we can write another sum involving g, the bijection g. This sum equals this sum f of g of y, where now y varies over y. Note one thing, that here we don't have any confusion about this sum. It is also a sum over a finite set, and that set is y. And why do we say that y is finite? That is because it is given that x is finite and g is a bijection from y into x. So automatically y is also finite by the definition of finiteness. So we have this thing. Then there is another substitution. This is part 2. Let n and m be two integers related like this, and let x be this set. It is the set of all integers lying between n and m, including n and m. And you can see from the definition of this set x that x is a finite set. Okay, now if ai is a real number assigned to every element I in X, then we have this finite series ai as I varies from n to m equal to this summation over finite set. If this part looks a little weird, just note that ai actually is a function. It's a function from x into r, like what we should have in order to be able to write a sum like this. And that function maps I onto ai. So instead of writing a of I, we are just simply writing ai. That's how we write the outputs of a sequence, right? In this case, we have a finite sequence, of course. So the finite series is the same as the finite sum. Then part E. Let X and Y be disjoint finite sets. Disjoint means their intersection is the empty set. There is no common element. And let f from X union Y into the set of real numbers be a function. Then we have summation f of z as z varies over X union Y is equal to summation f of X as X varies over X plus summation f of Y as Y varies over Y. The author has used different symbols. Okay, here he is using Z, here he is using X, and here Y. If you want, you can use the same symbol also, X. Okay, it does not matter. Note one more thing, that these two sums they make sense because X and Y are finite, but this other sum also makes sense because the union of two finite sets is also finite, so X union Y is finite. So this is also a sum over a finite set, and this is the statement. This sum equals the sum of these two sums. Okay, then we come to linearity. Next, those of you who are familiar with linear algebra, they will understand why these next two parts are named linearity. The first one is linearity part 1. Let X be a finite set and let f from X into R, and there is another function g also from X into R be functions. Then we have summation of f of x plus g of x equal to summation f of x as x varies over x plus summation g of x as x varies over x. In this case, unlike this one, we don't have two sets, but we have two functions. But note that here we don't have any problem about the set being finite or not, because there is only one set x and that is given to be finite. But what about this function? This is also a function from x into r, and what this function does, you can give it some name. Its definition is like this: h of x is defined to be equal to f of x plus g of x. So this sum makes sense, and these two of course make sense, and this part states that this sum is the sum of these two sums. So that is linearity part 1, where we have addition of two functions, that is a sum of two functions. And in linearity part 2, we are going to multiply a function by a real number. G linearity part 2. Let x be a finite set let f from x into r be a function, and let c be a real number. Then we have summation of c times f of x. F is a function, so cf is also a function which maps x into c times f of x, and this product is also just like f, a function from x into r. So this sum makes sense, and this part claims that this sum equals c times summation of f of x. So these are two linearity parts, and then we have monotonicity. Let x be a finite set and let f from x into r, and there is another function P functions such that f of x is less than or equal to g of x for all x belonging to x, then we have these relationships are reflected in the corresponding sums also in this way. Summation of f of x as x varies over x is less than or equal to the summation of g of x as x varies over x. That is, if the functions behave in a monotonic manner like this, then their sums also behave accordingly. So that is monotonicity. And then there is one more, I, triangle inequality. Let x be a finite set and it's raining heavily outside. The rain never relents, and this be a function. Then we have the absolute value of this sum is less than or equal to the sum of the absolute values. So this is like your ordinary triangle inequality, that is this one. Where a and b are real numbers. The only thing is that it's like the extended one, where you don't necessarily have just two real numbers, but any number of real numbers. So these are some of the basic properties of summations over finite sets, and the proof, like the previous one also, we will see in the exercises, and it's the second exercise. So now after this we have a remark. This is remark 7.1.12. The substitution rule which one? C, I think. Yes. C can be thought of as making the substitution x equal to g of y. It's that thing where we have this bijection g from set y onto set x. It's that thing, that part. Hence the name. That is why it's called substitution. There is one more observation. These properties, when combined, tell us that we can rearrange the terms of a finite series. Precisely, now I am going to write what the author is saying. Hence the name. Note that the assumption that G is a, okay, so we have something else also to say about this. Note that assumption that G is a bijection is essential here. If you don't have a bijection, say your G is not 1-to-1 or not onto, or neither 1-to-1 nor onto, then you won't get the same sums. Those two sums on the two sides of the equality sign in part C here, they will give you different values. But why? So the author asks us to justify why. Can you see why the rule will fail? If G is, say, not 1-to-1 or not onto, it's very easy to see why that will be the case. If G fails to be either 1-to-1 or onto or both, then we don't get the same sum, the rule fails. So I leave that to you. Okay, you just take a concrete set X, a concrete real valued function with domain X, and a function G from another set Y into that set X, which is, say, not 1-to-1. There, that itself will give you an example of the rule failing. And then of course you can take another function G which is not onto, and you will see that you get two different sums. Okay, now moving on from proposition 7.1, 11, instead of stopping, the rain is picking up intensity. Anyway, C and D, we see that you can write this finite series also like this: a suffix f of I, where F is a bijection from this set to itself. It's very easy to see why that will be the case. If you are calling this set X, then this sum, this series, finite series on the left hand side, this will be equal to this thing by part C. And then by part D, in part D we have a substitution. So you can substitute I by f of I. Like what you have in part D, you can write in place of x, you can write g of y. So like that, in place of I, you can write f of I. And then once you do that, and this sum by part D will be equal to this sum, and then again you use part C to write this as a finite series. So you have these two things. Now what this tells you is that instead of going like this, where I varies from n to m, you can follow another order, and that order will be given to you by this bijection F. So you can change the order, you can rearrange these AIs and get another sum, but that sum will also be this one itself. Okay, so informally speaking, we can rearrange the terms of a finite series. Informally, this means that we can rearrange the elements of finite series at will. Informally, this means that we can rearrange the terms or elements, same thing, that is the AIs, of a finite series at will as we wish, and still obtain the same sum. Which is something that we normally just simply use when we encounter finite series. We use this thing, we can write the terms in any manner we want, and we don't even give it a second thought. But now that is, I mean, these things show that whatever we have been doing all along, that is correct and that is mathematically justified. Okay, now we go to double finite series. Now we look at double finite series a finite series of a finite series. That's what double finite series are. That is, if you can think of a finite series in which the elements or the terms themselves are finite series, then you get a double finite series. And see how these things relate to how they connect with Cartesian products. So we start up with a lemma. We will now have two sets. So this is lemma 13. Two finite sets, let x comma y be finite sets, and let f from x Cartesian product y into R be a function. Note one thing, that because x and y are finite sets, in the section that dealt with finite sets, we have already proved that x Cartesian product y is also a finite set, and in fact we know what its cardinality is. The cardinality of x Cartesian product y is the product of the cardinalities of x and y. Okay, so this is again a finite set, and we now have a function, a real valued function with x cross y as the domain. Okay, then we have this. Then summation. Okay, which one is he writing first? X, yes. X varying over x. Summation y varying over y, f of x comma y is equal to x comma y belonging to x Cartesian product y. Let us first of all try to make sense of what we have written here. The right hand side is okay. The f is a function from this set into R, and this is a finite set. So it is just our ordinary summation over finite set. But what about the left hand side? In the left hand side, let us first see what we have in this inner summation. In this inner summation, for each x belonging to capital X, this f of x comma y is a function from y into R. If you choose small x from capital X and you fix that x, then this becomes a function from y into R. But x actually changes, so you can think of these functions as parameterized by this variable x. If these things seem somewhat complicated sounding, you just simply think of it like this. For each x belonging to capital X, this f of x comma y is a function from y into R. What you have to do in the formula for this function is that you put that value of x, then the only variable that is left in that formula is y, and it becomes a function of y. So this is a function from capital Y into R. So that means this inner sum is well defined, it makes sense. Okay, now that inner sum will have some value. However, that value itself depends on this x, because we first of all chose x, then we put that x, and then we obtained some sum. Now if we change the value of x, the sum will depend on x. So this sum itself is a function from capital X into R. Whatever we have here inside these brackets, this inner sum itself is a function from capital X into R, and capital X is a finite set. So this outer sum is also a summation over finite set, and this lemma says that these two things are the same. So now we are going to prove this. The proof will be by induction on the cardinality of the set capital X. Because X is a finite set, its cardinality is a natural number, so we are going to prove that thing. The proof is like this. We apply what is the exact language? Let NO. So first of all, he names the cardinality n. Let n be the number of elements in X. And now we will use induction on n. Induction on n, that is, let P of n be the statement that this lemma is true. For any set X having n elements any finite set Y and any function f from X product Y into R. That's what P of n means. Okay. Why X is any finite set. Note that X can be several different types of sets. The only thing we have here is that X must have n number of elements. That restriction is also not there for Y. Y just has to be a finite set. We are not saying what cardinality Y should have. It can have any cardinality which is a natural number and any function f. We are now going to prove that this P of n is true for all natural numbers n. We wish to prove that P of n is true for all natural numbers n. The base case is P of 0, that is we take n equal to 0. When n is equal to 0, we have, in the text it's written that this statement is very easy, it's easy to see that it is true. However, we will actually see what goes on in the statement. In this particular case, this sum is equal to 0. Why? That is because if you go to the basic properties of summation over finite set, there in part A you will see that such a sum is 0 if the set involved is the empty set, and n is the number of elements in X. So if n is 0, there is nothing in X, so that means X is the empty set. So by part A we have this, and also this is equal to 0. Okay, why is this second sum 0? If X is 0, then by the definition of Cartesian products, X cross Y is, oh sorry, I said X is 0. If X is the empty set, then by the definition of Cartesian products, X cross Y is also empty. So again by this part A, this is equal to 0. So in this case, both the things are the same. Now suppose P of n is true for some natural number n. Now we need to prove the statement for n plus 1. So that means we will need a set with n plus 1 elements. Let X be a set with n plus 1 elements. Let Y be a finite set, and let f from X cross Y into R be a function. Okay, now X is a finite set having n plus 1 elements. So by lemma, what was the number? I keep forgetting these numbers. 369. X is equal to x prime union x naught, where x naught is some element in x and x prime is, you can guess what it will be. It's obtained by removing x naught from x. And this x prime has n elements. This entire part is coming from lemma 369. So, okay, now it's time for us to use the basic properties of summation over finite sets. First of all, by proposition seven 111 part E, we have this summation. Shall I be able to write the things here? Okay, let me see. X belonging to x summation y belonging to y, this is equal to, in part E we have that two sets x and y which are disjoint, and we are considering the summation over their union, x union y, that is equal to the sum of two summations, one over x and the other over y. Now you apply that to this outer summation. Now in our case, in place of that first set x, you have x prime, and in case of the second set x, you have the singleton set consisting of x naught. So what I will write another line. That is, we are considering this. This of course equals this because x is x prime union x naught, singleton set consisting of x naught. And the way we have defined x prime, that tells us immediately that these two sets are disjoint. There is no, that is the sole element x naught of this set is not here. So they are disjoint. So now using this part, we can write this outer sum like this. X belonging to x prime summation f of x comma y, y belongs to y, plus summation x belongs to x naught, that is singleton set x naught. But we should have mentioned this thing, no? By part B and B, let me just write another line for the sake of easy understanding. Applying part E, we have this. However, if we now apply part B here, then we will get plus summation f of x naught comma y. Now once you put x equal to x naught, which you can do by part B, this becomes a function of y. So this becomes a finite summation over the set y. Okay, so far so good. Next, oh yes, now by the induction hypothesis, now note that we can do something to this first term, this term and this term. So to this term we can apply the induction hypothesis. Why? Because now x prime has n elements. X originally had n plus 1 elements, x prime has n elements. But there are some things you should at least note here. Originally what did we have? We had a set x whose number of elements is n plus 1, and we had a finite set y, and we had a function which looks like this. Now we have something else, slightly different thing. We have x prime and we have y, and we have a function like this. Are these two functions the same? Strictly speaking, they are not the same thing, but this is actually a restriction of this function to what subset of x cross y? To this subset. You try to understand one thing. Just like x is the union of x prime and the singleton set x naught, x cross y is also the union of x prime cross y and this. And the f that you are seeing here is the restriction of this original f to this subset of x cross y. Okay. Where again, so this is a function from x prime cross y into R, and y is a finite set. So we have all the hypotheses that that are needed in order for us to be able to use the induction hypothesis here. So we can do that now. So although we use the same symbol f, but here this f is the restriction. It's technically not the same thing. The domain has changed. So we put a full stop here, a period here, and we continue by the induction hypothesis. This is equal to means the first term will change, and now in its place you can write x comma y belonging to x prime cross y f of x comma y. And this let us keep this as it is for now. Y belongs to y. Now we can change this one also, and we can do that like this by proposition 7.1.11 part C. This final thing is equal to this sum, summation x comma y varying over x prime cross y f of x comma y. Now in its place we can write this. The question is how, and the answer is that there is a natural bijection between y and this Cartesian product. You can pretty much, I think you can guess what that bijection is. By that bijection, any element in y corresponds to, or because it's a bijection, so we can write like this, corresponds to this ordered pair. Okay, so you just go to part C and you will understand how we are having this, and the reason is that there is a natural bijection between y and this thing. But now I have already showed that the original Cartesian product x cross y is the disjoint union of x prime cross y and this cross y. So now we can again apply part E of proposition 7.1.11 and we can combine these two, we can merge these two sums into a single sum, and that sum will vary over the entire Cartesian product x cross y. So this one ends here, and then once more we apply part E of our properties of summations over finite sets. So by proposition 7.1.11 E again, this is equal to and just to make things even more clearer, we write within brackets, note that x Cartesian product y is equal to x prime Cartesian product y union this, and these two Cartesian products are disjoint. This is the empty set, and because of these things we are able to apply part E in the first place. So that completes the proof, and this proof has an application, and that application is very important. May not be so important in the finite case, but when we go to infinite series, it will be very important. It has a name also. It's known as Fubini's theorem. It allows us to change the order of double summations. So the next one is corollary. I need ink. This will be 14th item. Fubini's theorem for finite series. And the theorem is this: let x comma y be finite sets, and let f from x cross y into R be a function. Then do I have enough space? We will see. Summation x belonging to x, summation y belonging to y, f of x comma y equal to summation x comma y. We haven't written anything new so far because this is exactly what the previous lemma claims, but now this thing is equal to another such sum where we change the order of the things. Instead of x cross y, we now have y Cartesian product x. The function we keep like this. Okay, there if you forget this subtle thing, if you here also you write y comma x, then there will be some problem. This one is x comma y itself, but the Cartesian product, in that we have swapped the sets. X and y have been interchanged, and this thing again by the previous lemma is of course equal to the series of the series Okay, so this is Fubini's theorem for finite series. Now the proof is not very difficult, and that is because we have in fact done what needs to be done in the previous lemma itself. So due to lemma 7113. It's enough to prove that this sum is equal to this sum. But there is in fact no need to prove this. I mean, we of course have to prove this, but it's just a matter of mentioning something. We don't really have to go through lengthy arguments. We have whatever we need to write here already. And what we need to mention is this, but this follows from part C of the previous proposition, one of the substitutions. And the bijection involved in this case is this. By the bijection H from X Cartesian product Y to Y Cartesian product X defined by this formula. Y comma X. So what I want you to do, we will end the proof here itself with just this mention. What I want you to do is, first of all, you show that this is a bijection, which is very routine and extremely easy, and then you go to proposition 7113 part C and try to understand exactly how we are getting this one from this one. Okay, you try to make yourself actually understand what is going on and how we are using this bijection. That is exactly, precisely what I am trying to say here is that exactly how we are using this bijection here in part C of proposition 7113 to obtain this sum from this sum. Once you understand that, the proof is over. In fact, that's what the author says. I haven't written it down here, that see exactly how we are getting this thing. After this proof, I think there is one more remark, and that remark I forgot to write. That remark is about Fubini's theorem for infinite series. That is not always true. Okay, when we go to infinite series and then after having infinite series, we have already discussed this, we have already mentioned this, that just like we can use finite series to define this kind of sums, we can use infinite series to define sums over infinite sets. So when we go to those things, there Fubini's theorem is not necessarily true, but we have to restrict the summations or the series involved to something called absolutely convergent series. We will see those things, and it's coming because this section is, the theory part is over. After that, in the next video, we will start solving the exercises, and once the exercises are over, we are going to move on to the next section, which has infinite series, and those things will come that we are talking about here. Sums over infinite sets, those things will come in the next chapter, in chapter 8. So with this I end this video. If you want to discuss about these things, you can write in the comment section below, or you can mail me at my address, which will be there. The link will be there in the description. Today is Sunday, so we have already once again gone through group theory, field theory, vector spaces. So this coming Tuesday, let us again do calculus. So that being said, see you on Tuesday. Have fun with mathematics. Until then, this is me signing off, Lucifer from A Mathematical Room. Have a nice night.